Hi everyone, so this is the last part of chapter 5 and it's really just a lot of concepts here. So the first thing that we need to talk about the kinetic molecular theory of gases. So this is review. We did learn this in first year chemistry. So according to the kinetic theory, it will help us understand the behavior of gases. So it is important to remember that it is just a theory. There are some things that are wrong with the theory, and it's important for you to know what is correct about the theory and what is wrong about the theory, okay? So you need to know what the theory states and what is wrong with it. The first statement has to deal with the volume of the gases. So it basically states that gases occupy zero volume, or they have no volume, okay? And that is according to the theory. All right, so gases basically have zero volume. The second statement, the gas particles are in constant motion. You can add constant, random, and rapid motion, so that means they're constantly moving around. The third statement, the particles are assumed to exert no forces on each other. So that means they have no intermolecular forces. And then the last statement, the average kinetic energy of a collection of gas particles is assumed to be directly proportional to the Kelvin temperature. Okay, so this is talking about a direct relationship between kinetic energy and temperature. All right, so I will tell you that there are two things that are wrong with the theory and two things that are correct about the theory. So let's think about it. Let's see what you remember. One of the things that is incorrect about the theory is statement number 1. So let's just kind of mark number 1 here. Okay, so let's mark it. You could put it like an X next to it or something. All right. Let's see. And then the other one that is incorrect is statement number 3. Okay, so you probably want to put another mark next to statement number 3. All right, the reason why those are incorrect because gases actually do occupy volume and gases actually do have forces. They do have intermolecular forces. Remember the intermolecular forces that we talked about? We talked about van der Waals, dispersion, dipole-dipole, hydrogen bonding. All right, so they do have attractive and repulsive forces. So those are the two things that are incorrect about the theory. Everything else is true. Yes, the gas particles are in constant, random, rapid motion. Yes, we know they're always moving around. And yes, the kinetic energy is directly related to the Kelvin temperature, right? As temperature goes up, more collisions, therefore more kinetic energy. All right, now the other thing that you need to know, there is a mathematical equation that goes with effusion and diffusion. And you don't need to know how to solve it mathematically, but you need to understand it conceptually. Let's first take a look at diffusion. So if you remember last year, we learned about Graham's law of diffusion. So remember, according to Graham's law of diffusion, the lighter particles are going to travel faster. Okay, so the lighter particles travel faster. So let's write that down. Lighter equals faster. The heavier ones are going to travel slower, okay? And that is Graham's law of diffusion. Now the other one is effusion. Effusion is very similar to diffusion, okay? So the lighter ones are still going to travel faster, but the only difference is it's talking about like where the particle's moving through. Okay, so it says right here, it relates to the passage of a gas through an orifice into an evacuated chamber. So I'm going to draw a picture down here. So just imagine that we have a container, okay, and this right here is a wall separating the container. All right, so here's our container. All right, and then let's imagine that we have a hole. So let me draw a hole in the wall. So this is a hole in the wall, okay? Then let's say we have some particles in here. Let's say we have a big fat particle and then we have a small particle, all right? So effusion, how quickly it's going to travel through the hole, okay? So is this big particle here going to travel through the hole faster than the smaller one? Okay, and that's what effusion is. So let's think about it. Which one is going to travel faster through this tiny hole? Well, hopefully you guys have some common sense here. It's going to be the smaller one, right? The smaller particle is going to travel faster, right? The smaller particle is going to effuse faster than the bigger one through this tiny hole. And that's what effusion is. So you can see how it is very similar to Graham's law of diffusion, that the lighter ones are going to travel faster. The only difference is that effusion is talking about this chamber. Okay, what's going on in the chamber and what can fit through a small little hole. Okay? The last thing that I want to talk about today has to deal with this van der Waals equation. Okay, I'm just going to erase a little bit of this portion here because I covered up the equation. All right, so the van der Waals equation is for a real gas. Okay, so van der Waals equation is for a real gas. A real gas meaning that some of the statements here were incorrect, right? We have discovered that gases actually do occupy volume and gases actually do have attractive forces. They have repulsive and attractive forces. So the two things that are incorrect about the kinetic theory, that is a real gas, okay? Real gases have volume, real gases have attractive forces. So the van der Waals equation accounts for that. Okay, this van der Waals equation accounts for the things that are incorrect about the theory. If you look at this equation, you'll notice that it basically looks like PV equals nRT. It's just a variation of PV equals nRT, all right? So PV equals nRT, this is for what we call an ideal gas, meaning if everything about the theory was correct, then this is the equation that we would technically use, okay, if it was ideal. But a real gas, we use the van der Waals equation, okay? We take into consideration the things that are incorrect. So right here we have, you'll see there's a letter A here. That is what we call a correction factor. And then a little b over there, okay? That is also a correction factor. So you can see the N represents moles. So you can see right here, there's a correction factor for the volume. So that will account for the statement that says that gases have practically zero volume, okay? And then the other thing that was incorrect, remember, was about the attractive and repulsive forces. So you can see then there is a correction factor involving pressure, okay? So once again, you just need to understand conceptually that an ideal gas is if everything is perfect according to the kinetic theory. The van der Waals equation takes in consideration the statements that are incorrect right there about the theory. Okay, so it has volume correction and pressure correction because of the attractive forces. And even if we did a sample problem showing what the answer is using PV equals nRT and then do the math problem with the correction factors, the answers vary slightly. Okay, there's usually, I guess it also depends on the gas too. The larger the gas, the more it's going to deviate from being ideal. Okay, so there's not usually a huge difference in the two values, so that's why we typically just use PV equals nRT. But once again, usually depending on the shape of the molecule, the size of the gas, then therefore their correction factors will probably be larger and there will be a bigger difference, or we would say it deviates more from being ideal. All right, that is everything that you need to know for this last part of Chapter 5, and I will see you tomorrow. Bye.